Why does the Earth orbit around the Sun? Earth's nearly perpetual orbit around the Sun since the beginning of time, people have questioned why the Earth revolves around the Sun. The strong gravitational pull that holds the Sun and the planets in our solar system together provides the solution. The gravity of the Sun keeps the Earth in its orbit. Planets nearest to the Sun will have a stronger gravitational pull since gravity is highest at the Sun's center. This is the reason the Earth's orbit is elliptical, where it is at times closer to and other times further from the Sun. This dance will continue as long as the Sun exists, as far as we know. These days, it is not difficult for us to believe in such things because everything appears so commonplace and unimportant to us. But if we look back, we quickly see how challenging it was for humankind to develop this level of self-consciousness. Scientific ideas weren't as elementary back then as one may imagine. Learn more about the forces that keep the Earth, the Moon, and other planets rotating around the Sun by watching this movie with me. Spoiler alert, both exoplanets and exomoons are subject to the same laws. Historical background: since the time of the ancient Greeks, there has been the theory of heliocentrism, or the notion that the Earth revolves around the Sun rather than the other way around. The Earth was seen as the universe's center and the fixed point around which all the planets and stars rotated in the geocentric cosmology held by the ancient Greeks. But heliocentrism didn't start to catch on until the time of Nicolaus Copernicus. Astronomer and mathematician Nicolaus Copernicus wrote a book titled De Revolutionibus Orbium Coelestium on the revolutions of the celestial spheres in 1543 that described his heliocentric theory of the universe. His concept proposed that the planets rotate around the Sun and not the Earth in order to account for the observed motion of the planets. Galileo Galilei and Johannes Kepler were two other key figures in the advancement of heliocentrism in addition to Copernicus. Galileo, who had studied Copernicus' theory, was among the first to notice that Venus had lunar-like phases, which supported the heliocentric theory. Additionally, he studied Jupiter's moons and applied the concept of heliocentrism to describe them. The three laws of planetary motion, which Kepler, a mathematician and astronomer, established, provide a mathematically exact description of how planets move around the Sun. The Church, which adhered to the geocentric theory of the universe, was very opposed to the idea of heliocentrism. This ultimately resulted in Galileo being tried for heresy and the heliocentric theory of the universe being accepted. We now have advanced instruments like telescopes and satellites to view planets and stars more precisely, enabling us to better grasp the heliocentric concept and its consequences. Today, heliocentrism is acknowledged as a scientific truth. Observation-based proof. The discovery that planets' orbits around the Sun are elliptical by German astronomer Johannes Kepler strengthened the case for heliocentrism. He has made a significant contribution to science. He was the first to postulate that stars made up galaxies and moved in predictable patterns. His discoveries about the properties of light and the rules of geometry are still relevant today. He created the first modern telescope as well. But Kepler's three equations of planetary motion are what genuinely confound some scientists. The Sun is at one of two foci in every planet's elliptical orbit around the Sun, according to the first law. This one is almost boring because of how predictable it is. The second law states that equal regions are covered at equal times by a line passing through the Sun and a planet. This one is a little more intriguing. When a planet moves faster, it moves farther and farther away from the Sun. The outer planets of the solar system orbit more slowly than its inner planets because of this. The third law states that a planet's average distance from the Sun is proportionate to the square of its orbital period. The reason why this one is the most intriguing is because it enables astronomers to forecast the orbits of planets, moons, and asteroids. However, consider this, sometimes referred to as Kepler's fun law, Kepler's third law. This is so because astronomers frequently engage in a game known as Kepler's fun. Use the equation to determine how long it would take a planet to orbit the sun if it were twice as far away in order to win the game. It's a fun way to kill time and an effective approach to teach kids about the cosmos. Kepler's laws can offer important insights into the nature of the cosmos and how it functions for those seeking more than just a game. Let's simply play Kepler's fun for the time being, though. It's a fun and exciting way to learn about the solar system. Galileo Galilei's observational data may have been the most important factor in the demise of geocentrism. In order to examine the moons of Jupiter and demonstrate that the Earth was not the only body spinning around a larger object, the renowned scientist and professor carried out a number of experiments in 1609 and 1610. His observation showed that the planets revolved around the Sun, and he deduced that the Sun, not the Earth, was the solar system's center of gravity. Galileo's discovery contributed to the development of the heliocentric theory of the solar system. It also showed that the universe was more complicated and that heliocentrism needed to be added to our understanding of it. Therefore, we are aware that Earth, along with all the other planets in the solar system, revolves around the Sun. Will it ever cease, though? Performance of the orbits. The solar system is kept stable by the rotation of the Earth and other planets around the Sun. The Earth's orbit is essential to life as we know it. The Sun's gravitational pull keeps the planets in their orbits and gives us the warmth and light that are essential for life. It is exceedingly unlikely that the Earth and other planets will ever stop revolving around the Sun as long as it is still a functioning star. The Sun has existed for 4.5 billion years and is predicted to continue existing for at least another 5 billion years. As a result, the planets will keep on orbiting the Sun for a very long time. The planets' orbits do not, however, stay constant over time. The gravitational effects of other solar system objects can cause the orbits to steadily wander over time even though they stay stable. The eccentricity of Mercury's orbit, which progressively rises over decades due to the gravitational pull of other planets, is the most known example. The orbits of the planets can potentially be changed by outside influences. Sometimes asteroids or comets might pass by the planet close enough to change its orbit. A planet could drift away from the Sun or collide with another planet as a result of the smallest alteration in an orbit. In conclusion, even if a planet's orbit can alter throughout time, it will always be stable so long as the Sun is in an active state. Exomoons and exoplanets. What about exomoons and exoplanetary systems, though? The same physics and orbital dynamics apply to them even though they are much farther away from us. This means that many of the theories that underpin our understanding of the solar system also hold true for exoplanetary systems. Particularly, exoplanetary systems show stability comparable to that of the solar system. Exoplanets, like the Earth, are kept in orbit by the gravity of their sun. The exoplanetary system is held together by a strong force that maintains the planet's stability and stops them from drifting apart or colliding with one another. Exoplanets are kept in orbit by the same physical principles that control the behavior of the planets in our solar system, ensuring the same level of stability for those far-off universes. Interactions with other objects in the system may potentially have an impact on the eccentricity of exoplanetary orbits. As with Mercury's orbit in our solar system, this may result in the exoplanet's orbits drifting over time. Exoplanets' orbits may also be affected by outside forces such as incoming comets or asteroids. However, this is far less likely given how far away they are from the Sun. We haven't really witnessed an exomoon, thus we don't really know much about them. We are confident that they do exist, though. They really have to exist. If they didn't, it would be really strange. The search for an exomoon adds another layer of difficulty. Even smaller and more elusive than exoplanets, they are. It would be like attempting to find a single grain of sand near a headlight that was kilometers away. However, scientists from Columbia University think they may have found the first exomoon. One record stood out after Alex Tichy and David Kipping searched through hundreds of exoplanet detections in the Kepler data. According to the data, Kepler 1625, a star located 8,000 light-years distant, dimmed once due to Kepler 1625b, a planet the size of Jupiter, which was passing by. This indicates the existence of an extrasolar planet. Curiously, however, it had faded once more within a day, this time for a comparable period of time. It couldn't be the same planet because a single orbit should take about 287 days, which is insufficient time for the planet to complete in a matter of hours. Because a planet in a different orbit would move faster or slower than Kepler 1625b, it was most likely not a second planet. Moreover, a planet moving at the same speed as Kepler 1625b would share its orbit and presumably collide with it. Then, might this be an object that is closely following the planet? This could have been an exomoon. In conclusion, the same forces that maintain the equilibrium of our solar system also play a significant role in maintaining the stability of exoplanetary systems. This is the benefit of physics. As long as the circumstances are the same, the rules apply anywhere in the cosmos. The exoplanets' orbits are governed by the star's gravity, which also stabilizes their systems. The exoplanets will stay in a stable state for a very long period since the principles of physics still hold true, despite the fact that the orbits may wander over time. Realizing that the Sun's gravity and the Earth's orbit work together to keep us safe and secure in our own solar system is an amazing realization. So, keep in mind that the Sun's gravitational pull keeps the Earth in its orbit so that we can exist and flourish the next time you look up at the sky.